Let's take a look at another drag force scenario. So in this case, let's just take a box traveling this way with initial velocity v naught, and it's just going to encounter a drag force, and the drag force, just like before, is going to be a negative bv. Again, the drag force is going to be in the opposite direction of the velocity. So if we looked at a free body diagram, we're going to have the normal force up, mg's down, and then we have some drag force back, so some bv in the direction opposite the velocity. And so the question is, if you throw something, you start sliding something across the ground at, let's say, 10 meters per second, and it encounters this drag force, the drag force is always opposite the displacement, so it's doing some work on this thing and it's slowing it down, and eventually it stops. Well, the question is, how long does it take to stop? How far would it actually slide? All those are really good questions. What's the graph of the velocity look like? What's the graph of the acceleration look like? So let's start by looking at F equals ma. The only force we need to look at, because we're only going to look in the x direction, I mean, these two forces are balanced, is this negative bv equals m, and instead of a, it's going to be dv dt. So I'm going to separate these variables. Negative b over m dt equals dv over v, and then I'm going to integrate, and the integral of negative b over m is just negative b over mt plus some c equals the natural log of v. I'm going to use the initial value that I know that at t equals 0 the velocity is some v naught. So when t equals 0, that goes away and I get c equals the natural log of v naught. Okay, that's cool. Let's plug that in for what c is, plus the natural log of v naught equals the natural log of v. If those two things are equal, I can exponentiate. And again, I'm just doing algebra at this point to solve for v. The goal was the same. The goal was to take this differential equation and solve it. And by solve it, I mean get the velocity as a function of time. E to the negative b over mt plus this, well, e to the natural log of v naught is just a v naught out in front. And so then we get v naught e to the negative b over mt equals v, and we're done, because this equals to v is the velocity as a function of time. Think about what this graph would look like. This is our classic exponential decay, the velocity as a function of time. This says that the velocity starts out at v naught when t equals 0, and it just exponentially decays to 0. Remember, the slope here is the acceleration. It says the slope is always negative, so the acceleration is always negative. Cool, that matches with what we know. The acceleration is always going to be opposite the velocity here, right? The acceleration is decreasing our velocity. It's slowing down in this case, and we know that. We also know that the biggest acceleration is actually at the beginning, but that's true because the drag force is going to be the biggest when the velocity is the biggest. So the bigger the drag force, the bigger the acceleration, and again, that occurs at the beginning. Once the object starts to slow down, it's not moving very fast, well then the drag force isn't very much, which means the acceleration isn't very much, and look what happens to the slope. It's a big negative slope, smaller, and then eventually it just tails off. And I do know that the limit of the velocity as t goes to infinity is indeed 0. Now in the real world we know it doesn't actually take an infinite amount of time for this thing to stop, but that's what the calculus would predict. And then the better question is, how far does this thing travel? And the cool part is that we can use integrals as well, because we know that the change in something's position, in this case the same thing as distance, is the accumulation of velocity over time. Now we do have to integrate this from 0 to infinity, which technically makes this an improper integral, but that's okay. The velocity is a pretty easy exponential. We get this dt. The integral of e to the u, we just have to work with some chain rule issues. And again, if you need to, you probably should look at a u substitution, where you would make u negative b over mt, and then du is negative b over m dt, and you'd have to do a substitution there. And again, the result you're going to get is a negative v naught m over b e to the negative b over m t. And again, if you want to check that, just take the derivative of this and you get this, and evaluate that from 0 to infinity. When you plug in infinity, you get a e to the negative infinity, which is 0, and then you subtract this, and you end up getting v naught times m over b is actually the finite distance you would travel. Even if you include an infinite amount of time, you still only go this finite distance. But that's the distance the box would slide, given an initial velocity of v naught, given a drag force that's proportional to v and always opposite the direction, and then of course the mass. If you make the mass heavier, it would slide farther, because the drag force would cause, a constant drag force would cause a smaller acceleration, which would make it go farther, right? Bigger B, smaller distance. Bigger B is a bigger drag force. Bigger initial velocity, it would slide farther. Duh, it's moving faster at the beginning, same drag force, it would go farther. So these three variables are in the location we would expect them to be for this particular problem. I would expect you to be able to find the distance, find the equation for the velocity, set up and solve the differential equation, draw a free body diagram, look at the graph of velocity, and so on. Okay?